Yes, hello. Welcome to the wonderful world of atmospheric geology. We're gonna finish our atmosphere talk today. Actually, I'll show y'all. Like this kind of came up in the second period class yesterday, and I don't think we talked about it. It was more the global talk. Let's see if I can find it. Let's see. GM, electric car, 90s, 80s, 70s, 80s possibly. The EV1, yes. GM EV1. Let's see what Wikipedia has to say about it. Yada, yada. That's fine. All right. Uh, this is just an interesting story, and this kind of came up yesterday when we were talking about CO2 and climate change and CO2 levels. And we were kind of having a little discussion about, the individual and how if you want people to kind of participate in things, you have to give them an easy opportunity to do so. In the same way that don't mess with Texas doesn't work because we threaten people with a ticket, because nobody ever receives that ticket. It's not the threat of a ticket. It's a little bit of shame mixed in with an easy availability to throw your stuff away. There are trash cans pretty much everywhere outside of every business. And Texas has rest stops if you're making a long trip where you can kind of dispose of your stuff. And so we've given people alternatives rather than to just throw their trash out on the side. Doesn't mean it doesn't happen. Happens plenty of times, but maybe less than it would if we just didn't try anything at all. And so when you're talking about reducing CO2, you got to give people better alternatives. You got to give them better alternatives to buying hydrocarbon cars or one of the things that's going in, and it's very controversial. One of the things that's going in Texas, literally right through Palmer, I think, or really close to Palmer, is actually it is going to go through Palmer. Cans, I don't think I have any cans. Not today. Thank you. Uh, what's going to go right through Palmer in the next couple of years? Do y'all know what I'm talking about? The high speed rail. And it's not super popular around here. And I don't necessarily know why, but everybody seems to hate it and think that it's a terrible idea and it's only going to be bad. Um, and yet, when you go look at other countries that have high speed rails, they love it. It's a good thing that almost all sorts of people use. It's highly utilized and very popular. For whatever reason, and I could probably guess at those reasons, the United States has been highly resistant to high speed rail or things of that nature, probably because we have a huge auto industry, and the auto industry doesn't want you to ride on a public transport rail. We also have a huge airplane industry or airlines industry. They're going to fight against that as well. And so when we talk about reducing CO2 in electric cars, you can see that the latest electric car craze is widely popular. Tesla does not have dealerships where thousands of cars sit around. Like you buy a car and you have to wait for it to be made. Every car they make is essentially already sold and has been since their beginning. And so they're literally having trouble keeping up with demand. they're so popular, even though they're pretty expensive, and it's not a normal low level consumer car. But you look back and you kind of ask like, why did it take so long to get here? It's probably because the oil industry had things killed, like the General Motors EV1. I've heard about this like for a very long time. It was around in 1996, 1999, and it was kind of like a test out. From all accounts, it was extremely well liked. It was a pretty good electric car for what it was at the time. It worked well, had good range. People liked it. GM leased it to a lot of people to around it says around the Los Angeles, California, and Phoenix areas to see how the reception was. And reception was generally positive. And then GM, for some unknown reason, I think we could all guess, probably because they got lobbied by the oil industry, GM was like, nah, we're not going to do this. And basically took all the cars back and had them crushed. So literally, like, I'm not even going to let this car exist anymore. I'm not going to let the people who already have it buy it from me. If they want to have it, no, they cannot have it. Even if you like it, I will take yours away. I will take it to the junkyard and I will crush it so no one can have it. This was back in 99, like 20 years ago. And it's hard to look at their motives for that and feel like those are genuine motives. Like they were like, you know what, this just isn't going to work out well. To take a car and literally like wipe it off of the face of the earth when it was one of the very first possibly mass marketed electric vehicles seems very disingenuous. And there's probably a lot of details that need to be sorted through, but I've heard this for years and years and years now. And it's easy to look at on the surface and be like, they got lobbied by the oil industry to kill this because if electric cars take off, that's going to hurt the oil industry. And so, 20 years later, we're kind of back on track now. And with the popularity of Tesla, every single manufacturer, including GM, and all the high-end manufacturers, but every single one is working on an electric vehicle now. So more than likely, at some point in time in y'all's lifetime, you will drive and own an electric vehicle. I see them around. Does anybody's parents have a Tesla or electric vehicle or a hybrid? No. There's not too many around here, but if you make a single trip up into Dallas, you will see a Tesla on your way. They're fairly popular around. So I know there's a couple people in Waxahachie that drive and own them. So we talked about the CO2 climate chart yesterday, and that should be on the video. So moving forward a little bit, let's see. Human impact on global climate. What? Okay, so they're showing you the impact of each of these items. For a light bulb, you have 17,000 pounds of CO2 by using 1,100 kilowatt hours of electricity per month. For a light bulb, maybe what? I don't know. That's way too much energy for a single light bulb. That doesn't seem correct. I don't know what they're trying to say here. House using 600 cubic feet of natural gas per month. So that's maybe to heat your house. Trash, 1,000 pounds of CO2 by creating 4.5 pounds of trash per day. I don't create 4.5 pounds of trash per day. I think we create less trash than most people on our street, judging by the number of trash bags on the side of the road. But yeah, this is all maybe a little bit high. 8,900 pounds of CO2 by driving 160 miles per week. That's actually not too bad. On average, 160 miles per week divided by 7 days is going to be a little bit over 20 miles per day. Which seems reasonable. 1,000 pounds of CO2 by flying 1,900 miles per year. And this makes more sense to me. Airplanes are extreme polluters. Airplanes Diesel 18-wheelers, cruise ships, large shipping, not just cruise ships, but any kind of large ship is going to produce an immense amount of CO2. Very, very large fuel consumers. I wonder why that's crazy. That's crazy. You're telling me that a light bulb produces more CO2 than literally any of those other ones? I don't know about that. I don't know about that. That being said, especially around here, a lot of our electricity is still produced by burning coal, and coal produces quite a bit of CO2 that gets added into the atmosphere. So I don't know. I'd like a little context for this. In fact, let me see real quick, just because we got time, we can finish this. I'm gonna crack the book open, see what the book has any better context about this. Probably not, but what are we in? We're in chapter 11. And we're looking at this light bulb stuff. Human impact on global climate. There's the chart. There's another chart. No, I guess they don't have this in here. I figured they would, but they do not. No context. I need the context, please. Victoria, are you looking something up?
I'm looking that up. It says 1,558.
What, pounds of CO2? See, that's like way less than 17,000 pounds. Yeah, I don't know. Maybe I'll go in and delete that slide. I got at least give some context. All right. So sorry about that. I was just curious. I don't know what they're trying to get at here. It's not a very good graphic. If you create a PowerPoint or presentation, make sure it explains itself. It's easy to kind of read. What is this? What is this? Isn't even labeled. We got years at the bottom. We got surface water, global surface water warming, global temperature changes during the 20th century. Actually, it's not water, it's just global surface warming. Projected global average temperatures using different scenarios. And they don't tell you about the different scenarios, they just show you the four things. I do believe this is in the book. This is in the book, and it's right here. Can't lick my fingers anymore. It's not allowed. Here we go. To the right half, the shaded zone, each color line. Global average period. The orange line represents the scenario in which CO2 concentrations were held constant at values for the year 2000. So basically, if we stop increasing our pollution, we will be at the bottom line here. Probably the red line is if we don't do anything to change. I'd be interested to hear the difference between the red line and the teal line. Why does the teal line start out higher than the red line, but then kind of level off? I don't know. Again, not a lot of information about these. It only tells you about the orange line, which is a little sad. Science textbooks, everybody, they should have more information. Scientists want to know the details. I want the deeds. Why has CO2 level of the atmosphere been increasing over the past 200 years? Because we've been doing stuff. We've been industrializing. We've been burning fossil fuels, coal, natural gas, and petroleum. And we've been cutting down forests to make more room and make more farmland. And one of the things that you do have to remember, if you happen to get into global warming kind of talk and understanding the environment and trying to convince people to do better things, especially on a global scale. The United States has already gone through its industrialization. We've polluted the world heavily for the last like 200 years, and we've built all our stuff. We have huge cities. We had our industrial revolution where everyone was working in factories. We waged wars and we did all this other stuff, and we created a lot of CO2 in the process. Now we know better, and we need to be careful turning around to other countries that haven't been quite as developed yet and saying, well, you can't do this. Like, you can't do it this way that we did it because it's bad for the earth. They're going to look at us and be like, no, I need to get the same stuff that you have. Just because you did it first doesn't mean you get to do it in your own way. And now we have to follow all the rules. And that's kind of, I mean, it's a little bit different because China's been doing all sorts of stuff for a long time, but it's kind of the same way in China. China's still industrializing certain areas, and we're like sitting over here complaining about what China's doing, which is fair. But China has every right to do the exact same stuff that we did. You just want to find a better alternative for them to do it, and try to give them a trash can of sorts to kind of throw their trash away instead of just throwing it all over the place. So I think we need better alternatives to try to combat fossil fuel burning and greenhouse gas emissions. We'll see what happens. So temperature measurement, daily maximum measurement, maximum and minimum, and then there are other measurements: your daily mean temperature, your daily range, your monthly mean, your annual mean, and then your annual temperature range. Mean is just average, right? And then median would be the middle one. And so we look at the daily averages and the daily maximum minimum range. And we also look at records. So yeah. You want to keep an eye on your temperatures and see what they're doing here. What do we have a map of here? We have this is just an isothermic map. It doesn't really tell you if the map is a single day one or like, it's probably not average temperatures, with Duluth being down in the 31s and Bismarck being in the 19s. That's pretty cold. But it is probably just a single day snapshot weather map, or maybe like a month long average. When you see ISO at all, know that ISO means equal. So we have like isotopic lines. Isotopic, no. My brain messed up for a second. Anyways, if you see any line on a map that's called an ISO whatever line, that basically means that if you walk along this line, it will stay the same temperature. Like if I drive my car all the way pretty much from Raleigh all the way down near Monterrey, Mexico, and I stay on this line, it will be 80 degrees outside the entire time. That line is the 80-degree line. Same thing with this 70. I can drive along this 70-degree line and go all the way from the Atlantic coast all the way to the Pacific coast and never have it get hotter or colder than 70 degrees. And so the same thing happens with altitude. It's early. In the early days or on early class periods, I have hard times remembering words. It's an ISO for elevation. It's isotopic. This is a topographical map. Google isotopic for me, please. I think isotopic line is like if you follow a map and walk along an isotopic line, you will not walk uphill or walk downhill. It's not isotopic. What is it?
Yeah, it doesn't show anything.
Anyways, look up topographical map. Yeah, it's the elevation maps, and it should have like an ISO. Maybe put no, I don't know. I'll look it up in a little bit just to remind y'all. But anyways, an ISO line is going to be the same number for that value anywhere along that line that you get. So this is a temperature map, and we'll get into weather for our man, maybe I need some tea. Maybe I should have bought coffee. I don't know. Maybe I should have. I hate coffee, but for our signature assignment, there you go. Signature assignment. We're gonna do some weather map stuff. So we'll spend plenty of time getting familiar with the weather maps and how you read those. Why temperatures vary? The control of temperatures. It is basically based on how much solar energy you get, and a couple other important controls. So they have differential heating of land and water. The land is going to heat up more rapidly than the water. Water is really good at holding energy. And so if the water's cold, it's going to take a long time for it to heat up. Hence why you can turn your stove on and try to boil water, and it takes a while the more water you have. Also, water is very good at taking in energy, which is why we use water in our vehicles to keep the engines from overheating, because you can add a lot of heat into the water before it really starts to boil. So land gets hotter than water, land cools faster than water, and land gets cooler than water. The land is going to be much more variable in its temperature range than water. Water is going to be a lot more steady. So if you look at these two cities here, Vancouver versus Winnipeg, Vancouver is right on the ocean, and you can see that its daily temperature ranges, its yearly temperature ranges don't vary all that much. They don't get super high, they don't get super low. Where Winnipeg, which is further into the continent, gets super duper low and also has some pretty high highs up here during the summer months. And so a much greater temperature range in Winnipeg. I've heard it's awful to live in Winnipeg and Calgary. I've heard Vancouver's really nice though. It's like all the scenery of Seattle without all the craziness. Just nice Canadians and no crazy stuff going on, no chop zones or anything like that. Why other important controls on why temperature varies? Obviously, altitude is going to play a big factor. Your geographic position, what kind of cloud cover you get, and then albedo, how much reflection of the incoming solar radiation you get. So they have another comparison. We have Concepcion and La Paz, which I believe are both, well, they might be different countries, but La Paz is in Peru or Argentina. Okay, somebody Google that for me. La Paz and Concepcion. I know it's South America.
Bolivia?
Is it Bolivia for La Paz? Bolivia. What about Concepcion? Is that the same? I guess they both are inside this country here. So yeah, they're both going to be
Chile.
Oh, Concepcion's Chile? All right. So La Paz is Bolivia, Concepcion is Chile. Okay, good to know. We'll file that away somewhere. So you can see the temperature ranges. These two cities are pretty much at the same latitude. They're not. One's not any further north or south than the other one, but they have widely different temperature ranges throughout the year. La Paz is higher in elevation. It's up in the mountains. It also is going to have a higher albedo because of all the snow that happens in the mountains. It's reflecting quite a bit of the solar radiation. Probably also going to have more cloud cover. You go just to the other side of the mountain, not very far away, and you get to Concepcion, which is pretty much hot all year round. I mean, their average monthly temperatures don't really vary out of the 80s, just a little bit, like upper 70s sometimes, but not too much at all. Where La Paz is that cannot be right. Oh, those aren't negatives. My bad. I freaked out for a second. I was like, negative 40s, like your average range. That's just a dash. And so yeah, 40s to 30, so pretty close to freezing all year round up in La Paz. That's also pretty crazy. Temperatures never really get out of the 40s. That's interesting. Okay, so also it's going to be your cloud cover on an overcast day. You have lower highs and higher lows, if you will. And the lows, you might think, well, if the clouds are here, why, like, you wouldn't it shouldn't affect your low temperatures because you're not getting any sun. You should be just as cold as you would be on a clear day, but that's not actually true. I don't know if they're going to show this. They're not going to show this, but the clouds, imagine you have your clouds up here. Your Earth is actually radiating heat out. So we saw that it can radiate long wave radiation. When you have an overcast day, you don't actually get as cold in the morning because that radiated heat goes up and gets trapped by the clouds. And the clouds almost act as a blanket. Like in the morning, even though the room is cold outside, you have your blanket on and you're nice and warm underneath that. That's what the clouds on an overcast day do. So it's not just that the sun doesn't really reach you in the afternoon and you don't really get that warm up, but in the morning, the clouds also act as a blanket, so you don't really get that cool down early on in the morning. All that energy that's kind of left over from the previous day gets trapped in by the clouds. And I learned that from watching the weather in the morning. So there you go. How can cloud cover influence the maximum temperature of an overcast day? Clouds reflect a significant portion of sunlight. They reduce the amount of incoming solar radiation, and daytime temperatures will be lower. Wonderful. And then temperature maps. We're almost to the end. This is the last slide. Temperature maps are adjusted to sea level January and July. Used for analysis, represent temperature extremes. I believe they're going to show us a temperature map, hopefully. Global temperature patterns the temperature decreases poleward from the tropics. Yeah, obviously, near the equator, you're going to have higher temperatures. And it's going to get colder and colder towards the poles. Isotherms exhibit latitudinal shift with seasons. So obviously, when it becomes winter, our temperatures are going to drop, and in the summer, they're going to rise. Warmest and coldest over the land. So like they said before, the land has a greater shift in temperatures. The ocean is going to kind of hold its heat better than that. So I believe what we have here is a winter map for North America or for the Northern Hemisphere, and then a summer map for the Northern Hemisphere. So you can see that during the summer, your highest temperature ranges creep up higher up towards the poles. So we're included in the really hot part here. It also comes up into like Southern Europe, Northern Africa. In winter, the cold air kind of squeezes downward, and we're in the green range, the blue range kind of over here. And so you can see that the isotherms shift their latitude. They come down during wintertime, they go back up during summertime. Is essentially what they're getting at there. That's it. They do mention that near the equator, you don't have as big of a temperature swing from summer to winter because you're pretty much always getting a lot of sun. So in the middle here, if you're red in the winter, you're also obviously going to be red in the summer. But that's about it. That was all right. All right, so we will leave off there for tomorrow, where we will begin chapter 12. And don't forget, let's go ahead and do a reminder. Chapter 9 and 10 homework are out. And the 9 and 10 tests will be Monday when we get back. And then after that, we will probably go ahead and, while I continue to lecture on weather and atmosphere, we'll start the signature assignment and get that to y'all and kind of cover that so everybody gets a chance to work on that. So if you have any questions, is there anybody at home? Landon's at home. Landon, if you see this, I'm highly skeptical that you're going to watch the videos, but it's been that way for everybody. So if you see this, wonderful. Send me an email. Tell me I was wrong. But have a nice day.